Hi students, Professor Nugent here. In this video, we're going to discuss goodness of fit, r squared and adjusted r squared. Let's begin our discussion with r squared, and then we'll conclude with adjusted r squared. So for r squared, I want to think about what a low r squared means. A low r squared does not mean that our zero conditional mean assumption, the expected value of u given the x's, is not equal to zero. Okay, so this does not imply this. That we have a lot of error does not mean that that huge amount of error is necessarily related to our included variables. The low r squared does, however, mean that we have a large error variance and we'll have a potentially high variance of the estimated coefficients. So it may be hard for us to get a precise estimate of the coefficients. This may be mitigated if we have a large enough sample. Recall that the variance is the ratio of the estimate of the error variance to the total sum of squares times 1 minus that coefficient of determination from the regression of the variable on the other independent variables. So if you have a large enough sample, total sum of squares is going to mitigate a potentially high error variance. A low r squared also means that prediction is hard, right? Because there's a lot more going on that affects y that we are not controlling for. So if you are predicting about 2% of the variation in y, then there's the 98% of the variation is going to be important for predicting where y is going to go. So a low r squared makes prediction hard. All right. There's another caveat with r squared, and that is that r squared can never fall with an addition of an independent variable, some independent variable xj. So we often include with our goodness of fit measures adjusted r squared. We like to think about both of these because r squared has that intuitive interpretation of the percentage sample variation in y explained by the model, but then adjusted r squared imposes a penalty for adding additional independent variables using a degree of freedom correction. So what we'll see is that the adding the additional variables has to explain enough variation in y for the adjusted r squared to go up, so that the increase in the variation explained is more than the increase in degrees of freedom. Let's look at the equation and make that concrete. So we can write adjusted r squared as two ways. It's either 1 minus sum of squared residuals over n minus k minus 1 all over total sum of squares divided by n minus 1. And we can also write it as 1 minus r squared over n minus 1 all over n minus k minus 1. So you see that we have this degree of freedom correction happening here. And that as we add more independent variables to the regression, the denominator is going to go up. So for adjusted r squared to go up, we need r squared to go up by more than k. Then k is going up. Okay, so that is our adjusted r squared with a degrees of freedom penalty. Now, adjusted R-squared can be used for model selection of non-nested models, which is really great, as long as we have the same dependent variable. So model selection, non-nested models with the same dependent variable. So what do we mean by non-nested models? You may have y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 3 x3. And for another model, you may have y equals beta naught plus beta 1 x1 plus beta 2 x2 plus beta 4 x4. So neither model is contained within the other model. Let's write this as equation 1, this is equation 2. If equation 2 were just this, then equation 2 would be contained within equation 1, and we could use a t-test. If equation 2 were just this, equation 2 would be contained within equation 1, and we could use an f-test. When one equation is contained within another, then the model is nested, and then you can use an f-test. But if the equation is not, if one equation is not contained within the other, then you have non-nested models. Because you have the same dependent variable, then you can use adjusted R-squared to see which model explains the dependent variable better. All right, so that is it for goodness of. And let's conclude this video with a brief review of selection of regressors. We know that we want to control for unobserved stuff that's correlated with our variables of interest. We can do this using proxies, right? So if you have something like ability in your error term, and you are trying to get the effective education on wage, then you might try to think about some kind of proxy for ability, perhaps standardized test scores or some other proxy for ability that you want to bring into your regression equation to capture for the correlation between the proxy and the error term. Controlling for that then eliminates the omitted variable bias with your variable of interest. But you don't want to over control. So you don't want to bring in control variables that are going to make it hard to estimate the coefficients on your variables of interest in a precise way. An example might be if your variable of interest is income and you bring in another variable that is related to income, and so you're looking at the effective income perhaps on education outcomes, and then you control for something else closely related to income, then you're not left with much variation in income. So we would not want to control for income and something else related to income. And third, adding a variable that affects y and is uncorrelated with the x's is going to improve the regression, because you're going to get a lower standard error of the regression, a lower error variance, without the multicollinearity. So this is always a case where you want to bring in that variable. That's it for model selection and selection of regressors.